Yeah, so today's talk is going to be given by Mina Doosti from the University of Edinburgh. She'll be talking about quantum physical unclonable functions and their use in cryptography, cryptanalysis specifically.
Okay, thank you. Should I share my slides? Okay. Hello, everyone. My name is Mina Doosti. I'm a final year PhD student in the University of Edinburgh. I work with Elham Kashafi. And thanks a lot for having me here today. It's a great pleasure to be giving a talk for you in the quick seminar. So I will be talking about quantum physical unclonable functions today and their cryptanalysis. So first thing first, because you will hear me a lot during this talk saying PUF, I will set up the terminology first. So PUF, or physical unclonable functions, they are physical devices, or if you wanted the cryptography point of view, they're hardware assumptions that says that your device is very hard to clone, even for the manufacturer. And this happens in some physical devices because of the randomness that happens during the manufacturing of the device, which is uncontrollable in the nature. And as a result, you have devices that even the manufacturer cannot produce the two exact same copies of those devices. And we usually, PUFs, we usually treat them as some black box that we send some challenge into it and we get some response. And this challenge response have a unique behavior that comes from this physical property. And the sets of challenge responses, we usually call them challenge response pairs or CPR. And that's how we know the underlying functionality of these devices. And so PUF came from classical hardware security, or I should say electrical engineering, where in some circuits you can get these behaviors like that. But they extended into optics as well. So apart from electrical PUF, like arbiter PUF or things like that, which I will not talk about today, we also have optical PUF. And also they are interesting for industries. So even Samsung use PUFs in some of their chips in their smartphone. So that's basically the whole general overview. But I will not talk about in general PUF today. I will talk about a very specific class of PUF, which is quantum PUF. And these are the topics I will try to cover today. I will talk about why it's interesting to study quantum PUF. What were the first ideas and attempts to formalize or to bring this notion from classical security, classical cryptography to quantum? And then I will talk about a formal definition and framework to study quantum PUF and the security model that we have defined to study the security. I will talk about a very general class of attacks that we use as a cryptanalysis tool to break the PUF and to study their security, and also some possibility and impossibility results that are very general for quantum PUFs. And I'll talk about some proof techniques that we have used to show this possibility and impossibility results. And well, my talk until here will be mostly based on this paper, which I have also shared the link in the chat. And after that, I will briefly mention some of the applications of quantum PUF and some potential candidates for constructing them. I will talk about the relationship between quantum PUFs and quantum pseudorandomness at the end. So these two are basically mostly based on more recent works. So I will first start with why we're interested in quantum hardware assumptions. There are probably more reasons than what I just listed, but these are my 3 favorite reasons for studying quantum hardware assumption. The first thing is that so these hardware assumptions are usually very different set of assumptions that we know and we usually work with in cryptography, so they can potentially unlock interesting functionalities. In terms of practice, they are usually, or they're supposed to be, efficient and practical solutions for some applications like device authentication or things like that. And we'll also, when we go to the quantum world, we might be able to use some like physical properties of quantum systems in order to get advantage in terms of like our assumptions in cryptography and security. And more than that, well, I have my one foot in the physics world, one foot in cryptography world. And for me personally, PUFs are very interesting subjects to study. But why quantum PUF in particular, other than these are interesting things to study? Well, one main reason is that classical PUF in general, they have some problems or shortcomings. For classical PUF, when you use them as a key or a physical resource for cryptography, you cannot use each challenge more than once, because then it will be compromised and the security is broken for most of the application that we know. One of the most important problems is that most of the classical PUF are not secure. So they're vulnerable to machine learning attacks, and they usually produce a limited independent number of challenge response pairs. There are some classical PUFs that are promising, like optical PUFs, but so if you think about it, these devices are inherently quantum, so you can challenge them with, you can query them or challenge them with quantum state, and they can be vulnerable against quantum adversaries, so it's fair to study them in a category of quantum PUF. But also on the other side, in the quantum world, we have some properties that would be interesting and useful in the context of quantum PUF. For instance, we have, we know that we cannot estimate the classical description of quantum state with very few copies. And well, if our challenge responses are quantum, then we have no cloning theorem which protects them. And also we hope to get proof of security in some applications that we use a PUF as a primitive, which is something that we usually don't have in classical PUFs. And also quantum PUFs are interesting theoretically because they are somehow some quantum black box primitives that, well, you can study them. So these are like some motivations. The first idea to translate the PUF into the quantum world was something called quantum readout of PUF. And the idea for quantum readout of PUF is that you have a device, let's say that it's described by a unitary matrix, but unlike most of the times that you have a PUF, these quantum readout of PUF, the unitary matrix is public. So it's completely public unitary matrix, everybody knows that. And you rely on the unknownness of the challenges and responses in order to get the security. So the setting is usually like that. You have a verifier and you have a prover. The verifier sends some challenge quantum state. The prover interacts the state with the device. The device produces another quantum state because it's a unitary. And this output quantum state, you send it back to be able to be verified by the verifier. And because this is going on in a quantum channel, you have a quantum adversary that sits in between. And its objective is to identify itself or himself as the actual prover. So send another quantum state psi r prime, let's say, that the verifier will accept. And well, the recipe to work with this PUF is quite easy. You either build a database or you have the classical description of the unitary, which is enough for you. And you prepare and send the challenge state. When you get the response, according to the classical description of the output, you measure them and you verify them. But there are several issues with this kind of PUF. So first of all, these are not formally defined and the security framework is not formally defined. More importantly, these are only studied against pre-prime recent attacks. And if you allow actually the adversary to be more than that, so if you allow the quantum adversary to have access to the quantum computer or have quantum capability, because the unitary is public, the adversary can just run the unitary. And well, hence these will not be secure. So that's why we have introduced a new formal definition, a new framework actually to study quantum PUFs. And we start from like very theoretically similar to some works that have been done on classical PUF. And we define a PUF as a pair of algorithms, a generation algorithm and an evaluation algorithm. The generation algorithm takes the security parameter and it produces a specific PUF with an ID. And you can think of like the generation algorithm as this algorithm that generates all the PUFs. So if you take all the PUFs, this will be a family of quantum PUFs, similar to classical. And the most important property of quantum PUFs in general is that their challenge and responses are both quantum states. So you can think of them as density matrices in Hilbert space or pure state in Hilbert space. And in general, the dimension of this Hilbert space can also be different, not the same. And well, the most important part, which is the evaluation function, is an algorithm that takes a specific PUF, takes the input quantum state and produce the output response, which is also a quantum state. And because we wanted to start from the most general framework, we say that, okay, this evaluation function is a CPTP map. Challenge responses are quantum state. And then we look at now what are the properties that this CPTP map needs to have in order to be considered as a quantum PUF. Well, in classical PUF, there are a list of requirements that your mapping needs to satisfy so that you say this is a PUF. Well, actually, the list is usually longer if you look at classical PUF papers, but these are the essential requirements that you absolutely need to have in order for your PUF to work. The first one is robustness, which is that if you send the same challenge to the PUF over and over, you get the same response. So your PUF, maybe it has some sort of randomness, but it's robust against this behavior. And it's unique, meaning that if you have two different PUFs, they actually represent two different functions or map. And it's collision resistance in a sense that if you query the PUF with two different or distance challenge, it should give you two different outputs. It should not like always map you to the same thing. Otherwise, this PUF will not be useful for many applications like identification, for instance. And well, there's usually like another requirement, which also can be like different. Not in all the papers it's called that, but it's usually called mean entropy requirement, which is morally capturing the randomness or unpredictability of the PUF. And I showed it in a different color because this is something that we want to relax when we move to the quantum world. We don't want to like impose this requirement as a requirement of the PUF. So when we translate these requirements into the quantum world, because the challenges are, let's say, vectors in a Hilbert space or density matrix, it's not appropriate to just check the equality of them when we talk about robustness or collision resistance, but it's better to capture the distance between these quantum states. So that's why we define the robustness and collision resistance with indistinguishability, which in fact is a distance requirement between the challenges or the responses, and this distance we define with respect to fidelity. But in general, you can define it with any quantum distance that you want, like trace distance, for instance. And then we have uniqueness, which is a bit different from the other properties, because here we talk about the distance between two quantum maps or CPTP maps. And well, this is usually the language of quantum information is captured by diamond norm. So we require for each two PUFs that we draw from the family that they satisfy some distance delta U in the diamond norm with high probability. So these are now the requirements that the PUF needs to have in order to be a PUF, a quantum PUF. That's the formal framework for defining. Now, if you look at the requirements that I just told you, it's not hard to see that if you want the robustness and collision resistance to both be satisfied strongly, and by strongly I mean that you want to have the same distance for instance, for collision resistance when you have two outputs, you want to keep the same distance, and you want it to be satisfied for all the degree of delta C. And if you want this condition to be satisfied in this degree, then your map needs to satisfy the distance, which means that it should be a unitary or very close to unitary. This is something that it's formalized better in this theorem that says that if you have a channel E, which is consisting of a unitary map plus always arbitrary but contractive channel, and then this is a PUF if and only if the parameter epsilon is negligible in the security parameter, meaning that it should be very close to unitary. So hence we conclude that with the definition, the framework that we have for the PUF that we want to satisfy strong collision resistance and robustness needs to be a unitary matrix. But is it that any unitary can be a quantum PUF? Well, no, because there's like another requirement, which this is actually the physical assumption that we use for the PUF. And this needs to be also satisfied and formalized. And this unknownness or unclonability of that comes from the hardware of the PUF, we capture it with this definition or this this assumption called unknown unitary. And unknown unitary is basically a single shot indistinguishability with Haar random unitary. So we require the PUF to be on single shot before doing any query on any given quantum state that we select at random to be indistinguishable with the Haar measure. So in fact, the output, the probability of the adversary in producing the output should not be non-negligibly better than what happens when you give it a Haar random unitary. And what I want to note is that this condition is very minimal, because it simply ensures that the unitary of the PUF should be unknown before doing any query. So you don't have any previous knowledge on the description of the circuit or things like that on your unitary matrix. So for the adversary, the only way to gain information through the underlying functionality of the PUF is to query the PUF. So that ensures that the qPUF should be a unitary black box. That's the formal way of saying that the qPUF should be a unitary black box. And well, in that regard, is weaker than the requirement we have for classical PUF in terms of mean entropy. So we don't need that in quantum PUF. Another tool that we need for quantum PUFs to work is an efficient quantum test algorithm that allows you to check the equality of two unknown quantum states, because if the mapping of the PUF is unknown, then the responses that it produced are also unknown quantum states. So you need to be able to check that. Unfortunately, well, in quantum, we have such algorithms. So for instance, we have swap tests that checks the equality of two unknown quantum states with this probability. And there's a generalization of the swap test, which we extensively use throughout our work, and we call it generalized swap test or G-swap test. And it works when you have one copy of one of the state and multiple copies of the other state. And well, you can you can check the equality with a better probability. So these are the tools that we use for the testing part for quantum PUFs. And then we can define the security framework for quantum PUF. So the security property that the quantum PUF needs to have for many applications is unforgeability. So we want the PUF to be a device like a key or something like that, which you cannot predict the output of it. And this unforgeability is captured. We capture it with a game-based framework, with a game between an adversary, a quantum adversary, QPT adversary, and a challenger. And there's a learning phase where the adversary gets access to something like Oracle access to the qPUF, and it can query with any arbitrary, presumably adaptive quantum states, sends 1 to k quantum states to the challenger, and challenger reply to them with U applied on the challenge. So it the output sends back the output. And after that, there are challenge phases, which we have different types of challenge phase, and different types of challenge phase correspond to different levels of security. The strongest one, which is the usual unforgeability that, for instance, we have for MAC or digital signatures, is existential unforgeability, where we don't want the adversary to be able to forge even for a message that he picks, which here will be even for a quantum state, for a quantum challenge that he picks. But in order to avoid some trivial attacks, you have to check or you have to impose some condition, again, in distance, so fidelity or trace distance with the previously learned queries. And then we have a weaker level of security, which is called, in the context of PUF, is usually called selective unforgeability. In some other literature, it's called universal unforgeability. And this is when the challenger picks a challenge uniformly at random. So now that, again, we are in the quantum setting, uniformly at random means that we sample it from Haar measure. And the adversary needs to respond with, to produce the response of this challenge. And then there's a guess phase where the adversary produces forgery and the challenger tests the adversary state with the actual response of the PUF. And the adversary wins if the test passes the test algorithm with non-negligible probability. So that's basically the framework, and we study the security or unforgeability of quantum PUFs as a primitive inside this framework. Now, before I talk about our results and like security and the impossibility in the security, I will talk about a class of attack which we call quantum emulation attack. So it's not a, let's say, single attack, although we use a very specific algorithm for it, but it's actually a new class of attack which you can use against any black box primitive. And the idea of this attack comes from the difference between emulation and simulation. So in simulation, you usually want to produce or reproduce the map. So if you have like a unitary, you want to reproduce the same dynamics of your map. But in emulation, you actually don't care about reproducing the same dynamic. What you care is that for a given quantum state, the output of the algorithm that you make is actually very close to the actual output of the dynamic. So you don't want the whole action or the dynamic to be the same, but on given quantum state or a set of given quantum state, you want this to obey the same, like, or reproduce the same output. And well, the first time I was studying this and I've been part of this, and I thought that, oh, actually, this is very cool because this looks like exactly a notion of an attack over things like PUF, where we know that it's very resource intensive to simulate an actual quantum PUF, because you have to be able to simulate the whole Hilbert space or the whole unitary, but you can emulate it some if you have an efficient algorithm for that. So the algorithm that we use in our work to show this type of attack is a specific algorithm called Universal Quantum Emulator. It's by Marvin and Lloyd. And it's been initially introduced as a tool for process tomography. And well, you can see that, well, if D is the dimension of your unknown unitary, and a small d is the dimension of your sample subspace. So you have an unknown unitary on a large dimension, and then you have a set of input and output of that unitary as a sample set. And well, if you wanted to do tomography with that sample size, emulation actually gives you much more advantage. So you can see that against incoherent methods, universal quantum emulation is much more efficient to do that. And well, you can see the circuit of the algorithm on the left. And well, the idea for this algorithm is actually quite interesting. It works almost like a extended version of a Grover algorithm, where you want to amplify the probability of finding your state in somewhere specific, but in a very specific subspace instead of like on a specific state. And so the way it works is that you have a number of ancillas that they are all in the minus state, and then you have your input state to the algorithm, and you have your sample set. So you make these gates here according to your sample set. So you make them first of all, you use the input samples, and you create this controlled reflection gate, which I will talk about a bit more in the next slide. And by repeating to do this in blocks, you actually project your state into the subspace of your sample while encoding this information in the ancillary state. And then after these two steps, which is one for checking and one for like injecting the output of this specific state, which is the reference state, you do everything now in the reverse order. And when you do it in the reverse order, what happens is that because this in the step 4, you use the output quantum state for each input sample that you have used. While you do retrieving back the information from psi, you actually apply the unitary on the subparts of it, so that the state that you get out of the emulation at the end is very close to the action of the unitary on your state psi. So this is the general overview, but well, in order to work with it, we had to have a closer look at the algorithm because, as I said, this has been used as a process tomography tool, and the sample state are random input and output of the unitary. But we wanted to use it as a cryptanalysis attack, meaning that the adversary now has control over what kind of samples to pick. So if we look at we look at each block, we will see that, okay, so we have this control reflection, which reflect the quantum state about this state phi, which are in fact the samples. So this phi are either phi r, phi 1, phi 2 till the end. And what you can see is that the fidelity of the output state at the end, so the fidelity of the state that you get here as an output, is in fact very related to the success probability of your state being successfully projected into the subspace. So if the first step of the algorithm, which is here, if it works successfully, then with a very good fidelity, you get an output state here. Sorry. Yeah, so if your state, as a result, if your state is your state psi is fully spanned in the subspace of your sample, then the quantum emulator work with probability almost 1. So, but these are the things that you can see by looking at the circuit. But we have other observations as well. One was that, well, if you analyze each step and you want to work with a small sample size, you will see that so first of all, you can also have states that are not fully spanned in the subspace, but you can get some fidelities which are good enough for your attack. So you don't need the state to always be fully spanned in the subspace. And also, what we realize is that, so one of the properties of this algorithm is that, I need to go back here, that at the beginning, you pick one state at random, and in each block, you will always do 2 reflections. One is around a sample state, and one is around that specific state. So there's one state that you like repeatedly reflect about. And this state, which we call reference state, it turns out to be very important because this asymmetry that this algorithm has over the reference state helps us to use the reference state wisely. So let us to help the adversary to find a state which has actually a better property that when you do the emulation with a small sample size, you get a better fidelity. Well, and yeah, so after that, we wanted to find the output form, like a structure of this algorithm after k steps, so that we can play around with the reference and other sample states. So that's what we did. And we have shown that after k block, you can write the output of the quantum emulator as an expansion like this. And what you can see is that, well, you with some probabilities, you find the state in the state of the reference state here, 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 and here. And this happens with a probability that depends on the overlap of your state with the reference state and your state with other samples. But the cool thing is that it always, like, this part of the output will always remain the same, which plays an important role in the emulation. So, like, based on this knowledge that you gain by looking at the emulation algorithm, then we can have our impossibility result. The first impossibility actually has nothing to do with the emulation. It's just if you allow unconditional exponential adversary, there's no way that you can have security for unitary quantum PUF because any unitary can be learned in exponential time. But the second result says that you cannot have any unitary quantum PUF that satisfies existential unforgeability, and the reason is that you have a very small emulation attack with actually one block that breaks the existential unforgeability for PUF. And the attack actually works like this: you pick any random challenge state, and you pick a superposition of these challenges with another state. And if you're allowed with the degree that I told you in the framework, if you're allowed to have, let's say, almost like half overlap with the learned subspace, then you can pick a state like that which is the superposition, the uniform superposition, as your reference state for the emulator. Now, if you do one block of the emulation and you do the whole algorithm with just that one block, then you can see that the fidelity with these two specific states will become 1. So you get an output state for a new state phi3, which is, well, exactly equal to u phi3. And well, this shows that if the adversary is allowed to pick both the state and the challenge state, then there's no way that you can make this secure. So you don't have this level of security for quantum PUF. But the emulation also, so this was like the easiest emulation attack that I showed you, but it actually says much more than that. So if you have, let's say, a quantum PUF or quantum readout of PUF, or any PUF that you somehow make the database public, or the adversary has some knowledge over the database, you can not even have selective unforgeability in those cases. Because what happens is that adversary having knowledge over the subspace can make a quantum emulator that works exactly on that subspace. And then because this quantum emulator is efficient, it can always produce the response to any quantum state that you send inside that subspace. Because of that, you cannot have this level of security. And this sort of attack, they require more resource. So they're not like exactly Niski attacks, but they're still QPT. So you have still QPT adversary, but you need to do like K-block quantum emulation. But this is not the end of the world for quantum PUF, because we have positive results. We show that any unitary quantum PUF, which is unknown unitary with the definition that I talked about, it's selectively unforgeable. So as long as you pick any unknown quantum PUF and you pick your challenges uniformly at random from Haar measure, then you can have a selective security or selective unforgeability. And the good news is that this is usually the level of security that you need for applications that are based on PUFs. So that's good news. And the intuition behind why this happens is that, well, the quantum adversary, no matter how smart it picks, it learns the unitary, his dimensionality of the subspace will be bounded, and that the probability that it successfully produces an output quantum state is bounded by d over d over which, you know, like the big D is the dimension of the unitary and it's exponential in D. Well, but actually, so like intuitively, this is very intuitive result, but to actually prove that it's not that easy, what we needed to do, so I will go over like just some like general steps of the proof. And we need to abstract the notion of the test. So I told you that you can use quantum tests like swap tests or things like that, but in order for proof to go easier, we need to abstract the notion of the quantum test as a general quantum algorithm that takes K1 copies of one state, K2 copies of the other state, and with some probability, which is a function of the number of copies and the fidelity, it tells you that the quantum states are equal or not. Then we, after that, we define the notion of ideal test, which is if your fidelity between the quantum states is more than some threshold, it will always give you the answer yes as their equality. And then we try to find an upper bound for the selective for the success probability of QPT adversary. And we do that with the ideal test. And because we needed an upper bound, we also assume that the adversary over the learned sample, it has like full classical knowledge. But in fact, if you ever try to tighten our bounds, this is the condition that you need to relax, because this is actually not the case. But I mean, even given that, we can get an upper bound that is good enough. And then we generalize. So after like having this, we generalize back to the actual general test from the ideal test. And this is the theorem that we show. So we show that the success probability of selective unforgeability for a QPT adversary is bounded by d plus 1 over d, where d is the dimension of adversary subspace, which can go from 0 to d, a capital D minus 1. Well, and the proof idea is generally that that you can partition the Hilbert space into a Hilbert subspace that is always orthogonal to your space, and another subspace that has some overlap. And given that your challenge is selected from Haar measure, you can use the symmetry of the Hilbert space and the geometry of the Hilbert space actually to show that the probability that this in an average falls into the subspace that has no overlap is high, or the other one is low, is bounded by D over D. And then we show that by taking the integral over the Hilbert over the Haar measure, we show that the average fidelity of any state that a QPT adversary can produce in a subspace that is orthogonal to the state is actually very small, also bounded by 1 over capital D minus D. And putting all these results together, we can get this bound that you see here, which, as I said, is not a tight bound, but it's enough to show that you have selective security for quantum puffs. So I will briefly mention some applications and potential construction of the puff after seeing the framework and the possibility and impossibility result for them. So I'll start with constructions. So one potential construction that you can think of is that magically you have a family of unitaries or quantum puffs that are Haar random, or you produce a family of unitaries that are Haar random, and this will obviously these are good quantum puffs. They're secure, they satisfy all the requirements, but this is not a very efficient construction, as we all know. So there have been attempts to making this construction a bit more efficient by replacing this with T-design, and it's based on this work. Then they have used some recipe of circuits to construct a specific form of T-design, and they have shown that, well, this satisfies all the requirements that they need for quantum puffs. But again, this has some other problem, which is that because these are T-design, meaning that the circuit is somehow noun, so they satisfy the functionality of the quantum puff, but they are not quantum puff in the sense of hardware assumption. And then another potentially very good construction is still optical puffs, although like for instance the one that has been introduced in this paper is not secure in the framework that they introduced, because you can show that you can apply emulation attack exactly on the framework that they use the puff. But the puff itself as a primitive, as an optical device, can still be studied and can still be, maybe in some cases, can still be shown secure. So optical puffs are still good candidate potentially for quantum puffs. Then in terms of application, one of the most important applications of puffs in general are identification. And so here I show two quantum puff-based identification protocol. These two are based on this work. And well, we have shown two protocols. One is for a high resource verifier, like let's say a quantum server that wants to identify a low resource prover. And the prover only has a quantum puff. It doesn't have any other quantum computer or quantum capability. It only has this device. Well, in the other case, you have a low resource prover that has very limited capabilities, but not a quantum computer, and you have a quantum server, which also has a quantum puff inside it. And well, these two protocols enable you to identify the quantum server or the quantum client. And well, in both cases, you can show that relying on the selective unforgeability of quantum puff, you can show that in polynomial number of rounds, you can get security that's exponential, meaning the success probability of the adversary is exponentially low in the number of rounds. And well, the downside of this protocol is that they both need quantum memory for the quantum database that is used to check. But well, yeah, the security is good. And then in the second case, where you have like low resource verifier, you can do a completely classical verification on the verifier side, and you can delegate the whole quantum computing part to the server. yeah, so this is one application of the quantum PUF, and it can also be generalized to other applications like applications in quantum network like ping tests or things like that. I will not go through the details of this protocol. It's just for you to see what kind of functionalities they have. Another potential construction for a PUF is a hybrid PUF, which in fact is a combination of a classical PUF and some quantum device, presumably quantum preparation device. And it takes as input a bit string, a classical challenge, and it produces BB84 state as response. And well, although this PUF may look very weak, and it's in fact weaker, much weaker than the general quantum PUF that I have defined, if they are used in a correct way and with good with some other techniques on top of them, they can be also shown that they're very secure. And well, the idea is that we use them inside a frame inside a construction called hybrid locked PUF. And well, the idea is that you have two parties, and each time for identification, one party sends a classical challenge, but also a part of a quantum response. So let's say half of the response, for instance, which is encoded in this BB84 state. And then the locking mechanism can check this first half, and then based on the output produced from the classical challenge, it can produce a second half of the response. And the second half of the response enables the other party to check the identity of the first party. Now, the advantage of this whole mechanism and this whole construction basically is that, first of all, this construction is very, very practical because it's, you know, you only need to be able to do QKD to be able to do this protocol. And well, although this like underlying classical PUF may be weak, this double authentication way somehow that is used in this protocol enables you to get security against powerful adversary, because it somehow reduces the power of an adaptive adversary to the power of a static adversary. Because every time this party that has the PUF gets the query, it also checks that the query is coming from the actual server. And this, if there's an adversary in between, it cannot pass this check, and that's why the adversary cannot query the PUF in any way during the protocol. So that's also like another idea for having quantum PUFs. And now finally talk about the relationship between quantum PUFs, or the assumptions that we have in quantum PUFs, with pseudorandomness. Pseudorandom quantum state and pseudorandom unitaries are quantum analog of pseudorandomness that we have in classical pseudorandom functions or random pseudorandom generators. And they have been introduced by Ji, Liu, and Song in 2018. And they are a set of keyed states or unitaries that can be efficiently constructed, but they are computationally indistinguishable from Haar random state or Haar random unitaries. And well, obviously they will have a lot of applications in cryptography and other fields. And it has been shown that you can generate pseudorandom quantum state under the assumption that you have quantum secure PRF or quantum secure one-way function. And this has been resolved. This result has been shown in these two papers that I show here. But then we asked that, is that it? Or can we also achieve quantum pseudorandomness under a different set of assumptions like hardware assumptions? And well, in this very recent work, we have studied this problem, and the answer is yes. Surprisingly, you can start with a family of qPUF, and you can show that this also implies quantum pseudorandom unitaries. And out of that, you can construct pseudorandom quantum states. But we also show that if you have a family of PRU, you can use them as quantum PUF. So this is like both ways somehow. So to be a bit more specific, the notion of unknownness in quantum PUF can be generalized to T-query unknownness. And well, this implies pseudorandom unitaries, this we have shown. But this is not very surprising because they somehow like talk about the same thing. But the more interesting result is that we have shown that if you start from uniqueness, which is another condition that you have in the context of the PUF, which is in fact you want to impose maximum. So this is like for almost maximal uniqueness, which is that you want in diamond norm you want to have almost maximum distance. And if you start with a family that satisfies almost maximal uniqueness, you can show that this family is also a PRU. And this is a condition that you can maybe have by hardware assumption. And well, the toolbox that we use to prove that is from random matrix theory, where we show that, well, if you impose this maximum condition on the diamond norm, and you look at the distribution that satisfies this condition, you get the eigenvalue distribution of this condition. They're distributed in a specific way. And we use a measure called empirical spectrum measure. And there's a very old result by Diaconis and Shahshahani that they show for how random matrices actually this empirical spectrum measure converges to uniform distribution over a unit circle, which is like you can see in this picture, and it's not the same for other distributions. And well, what we have shown is that this condition imposing in the diamond norm also converges to the distribution uniform distribution over the unique circle. And well, in the limit, in the asymptotic limit, you can show that they converge to the same thing, meaning that they're computationally indistinguishable. But probably this can be also generalized further. So probably if you don't assume also maximal uniqueness, so if you assume like less degree of uniqueness, you can still get pseudorandom unitaries. But this is an open question. We haven't showed that. We just show it for 2 minus epsilon, where epsilon is small. And another interesting thing is that you can we have shown that you can use pseudorandom quantum states instead of Haar random state inside the context of selective unforgeability, and you can show that these are enough. So you can with the quantum PUF. Or any unknown unitary, if you use pseudorandom quantum state, you can achieve unforgeability against any QPT adversary. And well, this is a nice relation between these things. And I will wrap up with some open questions and future directions that exist in this field. I think one of the most important open questions is that how to construct a PUF, a quantum PUF, that is secure, but it's also practical. Which helps us to close the gap between this all this theoretical study of quantum PUF and practice. The other interesting thing is to study a non-unitary quantum PUF. So we have shown that in the setting that we have defined, if we want strong collision resistance and robustness, the PUF needs to be unitary. But if you relax that condition, then you can also have non-unitary quantum PUFs. So you can also consider other quantum channels as quantum PUFs. And these are interesting objects to study as well for future works. Another interesting thing is that how you would certify a quantum PUF. So if a manufacturer comes to you and tells you I have, like, let's say, a family of quantum PUF, will you be able to certify that this is actually quantum PUF? And this relates to some interesting questions in the area of certification, like certifying unknownness or effective dimensionality of an unknown quantum process. Another direction that I have actually started to work on, and I found it very interesting, is that if we can, like with the spirit of using quantum emulation as an attack tool, can we use other quantum cryptanalysis, other quantum algorithms that have been used for different purposes, but we use them for cryptanalysis. So can we extend the area of cryptanalysis from Shor-Grover to quantum machine learning algorithm, or to efficient learning algorithm like this result of Huang and Preskill in 2020. And well, yeah, this is I think I found it very interesting for the field of quantum cryptanalysis. Also, in terms of foundation, it would be interesting to see the relation between cryptographic unclonability, which is related to quantum pseudorandomness, and physical unclonability, which is also we have shown that is related to quantum pseudorandomness. And the understanding the inherent relation between these things will be interesting, and it can find probably applications in foundations of physics. And well, finally, it will be interesting to study other hardware assumptions other than PUFs, and to see, well, the relation between those and quantum PUF. And with that, I want to thank you for listening.
Great, thank you. So are there any questions for the speaker? Okay, so we have a question from Amir Obatar. He says, thank you for the amazing talk. I may have missed this during the talk, but how many qubits are required for these qPUFs, and are logical qubits required?
So basically how many qubits required depends on what degree of security you want to have, because so if I maybe can go back to well, basically the security parameter for quantum PUF is related to the dimensionality. So for instance, here for selective unforgeability, this capital D is the dimension of your unitary, of the Hilbert space, which you apply this unitary on, and well, usually you want to have like exponentially small success probability of the adversary. And well, yeah, so that's how it relates. So for instance, if you're okay with, I don't know, 1.01% security, you might be happy with like 10 qubit PUF. If you want more security, you need to scale it up. But yeah, that's how it relates. So if let's say if your dimension is 2 to the n, then n will be your security parameter.
Other questions? So I had a question. So you were talking about various ways that the qPUFs could be implemented. I was wondering if you were to just take a random circuit, and I've heard of results along the lines of saying if a random circuit is of a sufficient depth, then it starts to take on random-like properties, starting to be similar to the Haar random transformation. I'm just curious if that's been tried or if it seems feasible.
So as far as I know, so this, I think this construction with the T design also uses random quantum circuits in like a specific way. But yeah, I think that would be one way of looking into the PUF constructions. But there is like one subtle thing is that if you use such PUFs that are based on like null circuits, then you cannot have security against the manufacturer itself, which is okay for many of the applications. But because the manufacturer actually knows all the circuits, so you cannot assume that the manufacturer itself is an adversary. While as in some other construction, for instance, if you take an optical PUF, assuming that it's a good enough quantum PUF, then you can also have security against the manufacturer. But yeah, so in the cases that you can hide the circuits well for the, for during the protocol or during the transition before the protocol, then you can use construction like random quantum circuits as well. But the only result that I'm aware of is the T design one that I mentioned. I don't know of like other new results in this area.
Okay. Yeah, and in the case where you are relying on the device itself to provide the randomness and for it to be immune even to the manufacturer, so there's an assumption there. So is it something along the lines of just saying that there's a certain probability distribution over the possible unitaries that can arise? I'm just curious what the assumption looks like.
Yeah, exactly. So so for instance, uniqueness is a requirement of the PUF. So if you say that you have, let's say, a generation algorithm that produces this PUF for you, you need to assume, in fact, that they provide uniqueness, or you have to do some statistical check to be able to check that they're in fact unique. And that was one of the open problems that I mentioned. Like if someone gives you, like, let's say, a set of unitary or transformation or anything and claims that it's a PUF, how would you be able to certify that? So like, how, if you don't want to assume completely the whole thing, to what degree you will be able to certify that this actually satisfies all the requirements that we want?
Other questions?
I was wondering if you could elaborate on why pseudorandom states were sufficient to constructing quantum PUFs.
So you mean like the latest result in the relation between pseudo-random quantum states?
Yeah, so the second
Okay.
directive we're talking about.
Okay. Yeah, so I think I talked about this direction, but the reason that, like, this direction also, if you have pseudo-random, is this one that you're asking, that the pseudo-random unitaries can be quantum PUF?
So I think later on you were talking about getting from the pseudo-random states to quantum PUFs, right? I think.
Well, no. So the directions that from quantum PUF you can get pseudo-random unitaries and then pseudo-random quantum state, but also from pseudo-random unitaries you can get quantum PUF. And the reason is that, well, you can show that pseudo-random unitaries are unknown unitaries very easily, because they're like, you know, the unknownness is just that they need to be indistinguishable to Harmer in single shot, and in fact pseudo-random unitaries are more than indistinguishable. So yeah, this way is actually quite easy. You can show that because they're unknown unitaries, so as long as they're unknown and they're unique, which you can show they are, yeah, we have also shown that they satisfy uniqueness. So they satisfy robustness and collision resistance by unitarity. You only need to show that the pseudo-random unitaries are also unique and unknown, which they are. So this is one of the results that we have shown. So they can be a family of quantum PUF.
So we had a question from Paul Fisher. Paul says, thanks for a great talk. I have a naive question that I think was discussed, but I wanted to clarify. So would a classical PUF from a classical computer have little security against an attacker with a quantum computer? If so, the implications for society seem pretty vast.
So I think the answer is that classical PUF are against sophisticated attack like machine learning. Most of them are vulnerable even against classical adversaries. So if you're able to run a good machine learning algorithm on a classical PUF, it's very likely that you break the security, because most of them, they can be modeled. But well, you can also, so in a very like theoretical point of view, you can study classical PUF in quantum security models, similar to, let's say, studying MAC in quantum security model, where you give quantum access to a classical function. But now, in this case, the classical function is the PUF. So we have not studied that, because initially they are broken against classical adversaries. So yeah, we actually don't have a provable or almost provable classical PUF that is really secure. Yeah, so I guess I hope I have answered your question.
Okay, so we're getting to the end of the hour. Final question before we wrap up. Okay, so we can end. Thanks, Mina, for a very interesting talk.
Thank you so much. Thanks for having me. It was a great pleasure meeting all of you. Bye. Good evening.